Okay, I forgot to record the meeting. Fine. Time domain representation. Sorry. Time domain response of low pass filter. So if I plan to draw the reconstruction block, where I have this m delta t, that is the sampled signal. So we basically need to feed it to this low pass filter, which is HT, and we'll obtain MT, which is the original message signal given as m delta t convolution with ht. So if we write the sampled signal expression, so that we have already seen, is nothing but the product of message signal with the infinite impulse train. Okay, made a mistake here. M times NTS. So when we convolute this with this sync function, that is the time domain response of this low pass filter, fst, we'll have this follows: sum over n minus infinity to infinity m nts, which is a constant part, sync fst. So while this part is constant, these two here are the functions of time. So we are basically convolving the impulse function with another time domain function, so that would result into the following. let me insert a slide here and write. So this is actually what your reconstructed signal is. So you can go one step further from here, minus infinity to infinity, and ts sync fst minus n, since fsts result into 1. So you can see from this term here, these are shifted sync pulses by integer multiple of sampling period amount, and the amplitude of the sync pulses are scaled by the original message amplitude at those particular integer multiples of fundamental period. So actually your reconstructed signal, which I'll denote as m hat t, we can see it's a summation of infinite number of shifted and amplitude modulated sync pulse. So if I am to draw the spectrum to visually interpret what how exactly we can recover MT from those amplitude modulated and shifted version of sync pulses, so this will look like as follows. So let me draw the first sync pulse corresponds to N0. So as I was discussing, this is the sync pulse corresponds to M0 here. M2, I'll next draw the sync pulse corresponds to uh, the pulse at the first fundamental period. I'll use some different color here. the important part to know that at this point the contribution to the sync pulse corresponds to n0 is m0, and at that particular point the contribution of the sync pulse, which is shifted by one fundamental period, is 0. So they are not interfering with each other. And this is the part where it's m n t, sorry, not nts, only ts. And you can see the contribution of the sync pulse corresponds to n0 is 0 at this particular case, where we are sampling corresponds to the sync pulse for first fundamental period. And this similar behavior will be observed for other sync pulses also. For example, if I plan to draw choose the proper color. The drawing is actually not very good, but you can assume you will have other sync pulses. But the most important is that for one particular sync pulses, the contribute where at the point where I am sampling corresponding to that sync pulse, the contribution from all other sync pulses are 0 there. So basically they are not interfering, and that is being ensured when you follow the Nyquist criteria. So this reconstruction of the original signal is being happening by interpolating the sync pulses only. So let me point it down here. This expression, if you look here, this is nothing but sync interpolation. You are using a number of sync function to actually interpolate the original message signal. So your interpolation filter is sync filter only. So the answer to the question here, where is that? Yeah. So when it comes to the original signal reconstruction, from the samples via interpolation, your interpolation filter ideally should be a sync pulse, because you are supposed to pass this sampled signal through a low pass filter, and this low pass filter is going to have a sync pulse time domain response, and when that is being convolved with the uh, ideal impulse train, so basically you will have your original signal as a amplitude modulated and shifted version of infinite number of sync pulses that you are going to use to interpolate the your original message signal. With that, let us move to our third question. So now we have a sinusoidal signal mt is equal to cos 5000 pi t, and it is sampled using a impulse train with sampling frequency of 8 kilohertz and followed by a low pass filtering with the ideal low pass filter of cutoff frequency 11 kilohertz. So what are the frequencies of the sinusoid that should be left after passing through this low pass filter. That is what the question asks. So let us first look at this cos function here, cos 5000 pi t. So this we can write also as sum of two complex sinusoids, and we have already seen that complex sinusoids in time domain is equal to shifted impulses. And what is the shift amount? Shift by the frequency of sinusoid in frequency domain. So when you talk about this time domain signal, sum of two complex sinusoid, which is actually our message signal also, the frequency domain representation is nothing but two spikes at frequency 2.5 kilohertz and minus 2.5 kilohertz. I hope this part is clear to you. So if I am to draw the spectrum of message signal MT, which is given as this MF, it consists of two spikes of both amplitude half. This is 2.5 kilohertz, this is minus 2.5 kilohertz. Now we next move into the part where it is being said that you are sampling this signal, and for this sampling you are going to use a impulse train with sampling frequency 8 kilohertz. Fine. Let us see how this will look like in frequency domain. Sampling is done using impulse train with sampling frequency 8 kilohertz. By the way, note that here that the sampling frequency is actually greater than twice the maximum frequency component is. You have 2.5 kilohertz is your maximum frequency component, twice that of is 5 kilohertz, but your sampling frequency is 8 kilohertz, so you are well beyond the Nyquist criteria, so there is no ideally not going to be a distortion. So we have already seen what is the spectrum of sample signal is going to look like. It's just infinite number of copies of the original spectrum. The amplitude is scaled version by with the fs, and the copies are shifted by integer multiples of sampling frequency. So that is all going to happen. So it is like, if we call it m delta f, the spectrum of sampled signal, it is, we have already seen the expression, it's fs times infinite copies f f minus n fs. So for this particular signal mf, if we try to draw it, what it's going to look like. So let us just try to write first 2-3 terms, like we are just ignoring the fs part as of now. So let's write f m f minus 2 fs plus, let's start with negative n, f plus fs plus m f plus m f minus fs plus m f minus 2 fs. So here fs is 8 kilohertz. So mf will remain this half thing, the spikes at 2500 plus del f minus plus 2500. Now we talk about f minus fs thing. So in that case we are going to have del f minus 2500 minus sampling frequency and plus del f plus 2500 minus sampling frequency. Similarly, talk about f minus 2fs. So in that case it's del f minus 2500 minus $16,000 and del f minus 2500, sorry, plus 2500 minus 16,000. The terms corresponds to f plus fs. What it's going to be, let us write those two. Del f minus 2500 plus 8,000 plus del f plus 2500 plus 8,000, and we can write the term corresponds to fs also. F minus 2500 plus 16,000 plus del f plus 2500 plus 16,000. So you can see this is a spike at 2.5k. Let us talk about the impulse functions at the positive domain. Then we will see the negative, and they will see this is just counterpart of what is being in positive domain. But first look at the positive domain. This one here corresponds to 10.5k, and this one here corresponds to 5.5k. This one here corresponds to 18.5k, and this one here corresponds to 13.5k. Similarly, this one here you can see corresponds to minus 5.5k. This one here corresponds to minus 10.5k. So you can see these are basically counterparts of their positive domain. And similarly here you can see this is 13 minus 13.5 and this one is 18.5. I'm not writing them. So let us introduce a new slide here, and draw the spectrum. So we'll have something at 2.5k. You have seen 2.5 kilohertz. We have at 5.5 kilohertz. We have something at 10.5 kilohertz. 10.5 kilohertz. We have impulse at 13.5 and at 18.5 kilohertz. Similarly, this is 0. Negative side we have here minus 2.5k, minus 5.5k, minus 10.5k, and so on. So there are multiple other impulses, actually infinite of them, but we don't actually need them because the question here says that this sampled signal is now low pass filter with the ideal low pass filter of cutoff frequency of 11 hertz, 11 kilohertz. Okay, so this entire thing is being passed through 11 kilohertz. So just a moment, the pen got hanged. Okay, it's back. So this is the sampled signal spectrum which is being passed through a low pass filter of cutoff frequency 11 kilohertz. So 11 mean it is somewhere here. So this is the cutoff frequency, sorry, this is the low pass filter, and this is the cutoff frequency of low pass filter. (11 kilohertz). This is minus 11 kilohertz. So if I have to find the sinusoidal components that low pass filter is going to pass, so rest of these things we do not care, similar in both domain, because the moment you are passing the sampled signal through low pass filter, these are filtered in actually, and rest of things are being just blocked. So you can see we have three frequency components, three sinusoidal components, one at 2.5 kilohertz, another at 5.5 kilohertz, and then the next one at 10.5 kilohertz. So these are the three sinusoids that the low pass filter will actually let pass. So we have to see whether there is any option for that. So yeah, the second option where we have 2.5 kilohertz sinusoids, 5.5 kilohertz sinusoid, and 10.5 kilohertz sinusoid, three of them. You can see had the question says that okay, the cutoff filter is now 7 kilohertz, then we are going to left with these two options, this 2.5 and 5.5, but the question says the cutoff frequency as 11 kilohertz, so we are going to have these three sinusoids. So second one is the correct answer. With that, let us move to the next question, which says that just a minute. Okay, the minimum sampling rate required to avoid aliasing for the signal empty which is given as sinc cube 20 pi t. So what is the minimum sampling rate required to do that? So first of all, I'll consider this function, not sinc cube, just sinc function 20 pi t. So sinc function in time domain, we can immediately see that the frequency domain, it's going to be a rectangular pulse. So let me write it down. Amplitude we can ignore here because it's not required. So frequency domain we are talking about. So two properties the sinc pulse in time domain is going to have. Frequency domain, first of all, it's a rectangular pulse, and second of all, it's a one-sided frequency, sorry, one-sided bandwidth, not frequency. Is going to be 10 pi. So this sinc pulse here have this frequency domain representation, which is a rectangular pulse which have a one-sided bandwidth of 10 pi. Remember, it's not I'm writing why 10 pi, not 10, because you see the sinc function is sine pi x. So we are given, sorry, sine pi x divided by x. We are given sinc 20 pi t. That means sine 20 pi square t. Correct? So from here you can see what is your band frequency component is going to be. You can separate 2 pi and you are left with 10 pi. So that is why you have to be careful here. Your one-sided bandwidth is 10 pi t. So now you have to find the signal, the bandwidth of the signal mt, which is a sinc cube actually. So it's let's say the frequency domain representation, we call it p, we denote this function as m dash of t. So it's p m dash of f. So now I have sinc cube of 20 pi t. So in frequency domain representation is of course going to be convolution of with itself 3 times. So we are not really worried about the shape, but what we are worried about is actually the bandwidth. Now bandwidth will become 3 times of the original one, 30 pi. You can actually see it from this expression here also, because sinc cube uh, of some function, let's say this is a, okay, just a minute, sinc cube of x basically means your sine cube x divided by x cube, and this sine cube x you can write in terms of sine 3x plus sine x. I don't exactly remember the formula, there should be some scalar term here, it should be 1 over 4 most likely. So basically the bandwidth will become 3 times here, so that would be actually reflected in the frequency domain. So your mt is going to have a maximum frequency component of 30 pi. So if you have to sample this signal and you also want to avoid aliasing, so basically you have to go for the Nyquist sampling criteria. You have to sample at equal or higher than the Nyquist rate. So that is going to be 2 times this maximum frequency component, that is 60 pi. So your minimum sampling rate need to be 60 pi hertz. So 4 is the answer. So this question here is says that you have considered a message signal with maximum frequency FM and the minimum sampling rate required to sample this signal to avoid distortion of the spectrum is termed as you pretty much know what it is. It is just the Nyquist rate only, because when you basically sample at the Nyquist rate, you avoid the overlap between the like different spectral copies of your original spectrum, so that way you avoid the distortion, so therefore no aliasing. So basically you have this advantage when you sample at a Nyquist rate and then you pass the sampled signal through a low pass filter, you will get your original message spectrum undistorted, so that actually leads to no information loss, or in other ways you can say no distortion. So the answer is going to be Nyquist rate here only. Now this is a bit of not very straightforward question. We are given a parallel resonant circuit. Can one of you please mute yourself? It's causing a big noise in my side. Okay. Okay, so we have a parallel resonant LC circuit. The inductor value is given as 1 mH and the capacitance is 50 microfarad, okay, minus 10 to the power minus 7 mt. So it's a variable capacitor, where mt is a message signal which varies slowly and the maximum value of message signal is much less than 1. So what should be the approximate carrier frequency of the resulting frequency modulated signal xt? Okay. So they talk about approximate carrier frequency, that is going to be equal to the resonance frequency of a parallel LC circuit. And when you talk about parallel sorry parallel LC circuit, the frequency you're talking about is 1 over 2 pi root over LC. So basically you have to compute this value here. So let us substitute those values. So L is 1 h, so 10 to the power minus 3, and C is 50 into 10 to the power minus 6 minus 10 to the power minus 7, okay, it's 10 to the power minus 3 here, 10 to the power minus 7 mt. Okay. next step, let us try to simplify it a bit more. We take 50 10 to the power minus 6 whole outside, so that will make it 5 into 10 to the power minus 8. Inside should be 1 minus 10 to the whole thing is taken outside, so it should be 1 over 500. Okay, 1 over 500 mt. Okay, so this 10 to the power minus 8 become 10 to the power minus 4, go above, fine. 10 to the power 4 here divided by 2 pi square root of 5, and then we have 1 minus 1 over 500 mt half, fine. And then we have 10 to the power 4 2 pi square root of 5, this part we keep as common, and then we have 1 minus 1 over 500 mt minus half here. Okay, so we are given that maximum value of the message signal is much less than 1. So actually this whole term is much less than 1, since it's 100 500 times already a pretty low value, times mt, which also takes value much less than equal to 1. So this thing we can approximate here as 10 to the power 4 by 2 pi root over 5 1 plus 1 over 1000 mt, and this is I am using this formula 1 over minus half 1 plus 1 over 2 x, and this can be used when x is much less than equal to 1. So we have our carrier frequency expression as follows: 10 to the power for this scalar term plus 1 plus this term. Okay, so fc here is the scalar part 2 pi square root of 5 1 plus 1 over 1000 mt. So mt value is already, amplitude is much less than 1, on top of that it is being divided by 1000, so this term here you can ignore, approximately goes to 0. So you are left with your carrier frequency expression as follows: 10 to the power 4 divided by 2 pi square root of 5. So let me use the calculator for this. So you can separate first of all this 10 to the power 4 thing, we can keep it 10, and then the 10 to the power 3 can go into the kilohertz, so it's 10 over 2 pi square root of 5. Let me just compute. 10 divided by 2 divided by pi divided by 5 square root of that, it's given as point okay, just a second, 0.71176. okay, 0.71176 kilohertz. So you can also write it as 711.76 hertz. So this is my approximate carrier frequency should be, and one of the answers should match with this. Okay, the second answer 7-1, fine. The second answer itself is matching, so this is what we are looking for. So next we look into this question again. We have the sinusoidal signal mt is equal to cos 500 pi t. It is being sampled using a impulse train, the sampling frequency of 400 hertz. Okay, first notice we have cos 500 pi t, right? So let us write it down, cos 500 pi t, and it can be written as sum of two complex sinusoid, that is e to the power j 500 pi t plus e to the power minus j 500 pi t, and this is in frequency domain. This complex sinusoid will just become some shifted impulse at 250 hertz and minus 250 hertz. Next we see the sampling frequency is 400 hertz. So one thing you need to be careful here, that our FM, that is the maximum frequency component of message signal, we see it's 250 hertz, sorry, not kilohertz, only hertz here, and this is the maximum frequency component of our message signal, and the sampling frequency fs is chosen as 400 hertz. So you can see that fs here is less than twice fm, as twice fm is going to be 500 hertz and sampling frequency is less than that. So in this case you cannot get the undistorted signal, or there is going to be a aliasing, that is the overlap between the spectral copies, so you are going to lose information. It may not be relevant in terms of question, but just observation I made here. So it says that when you sample use a impulse train of the sampling frequency, and then you pass it through a low pass filter of cutoff frequency 500 hertz. So what are the frequencies of the sinusoid present in the resulting signal? Okay, fine. So we have already the spectrum of the signal here, so let me graphically draw it. It's much easier to remember in that way. So here you have at 250 hertz, and here you have at minus 250 hertz. Then you basically pass it through impulse train, so your m delta f, that becomes scaled by fs, and then infinite number of copies, but the copies are shifted by a integer multiple of sampling frequency f minus n fs. So it is going to look like this. Okay, we ignore the scaling term here. Like before, I will write the only three terms here, that is the m f plus fs, another is m f only, and m f minus fs. So first pick m f plus fs. So what we are going to get here is del f minus 250, and fs is 400, so plus 400 plus del okay, better to take it to the next slide because it don't fit here, so just mf plus fs plus mf plus mf minus fs. So f plus fs, this is going to be del f minus 250 plus 400 plus del f plus 250 plus 400 mf then, which is pretty easy, f plus 250 and f minus 250, and then comes f minus fs, that is del f plus 250 minus 400 and del f minus 250 minus 400. So if I draw the spectrum of this sampled signal, it's going to be look like this. Okay, first I'll remove this one. We'll have this at 250 and minus 250, so I'll draw these two first. (250) minus 250, and then this one is here at 150. Okay, this one is here. Okay, this one actually corresponds to minus 150 and this one corresponds to 150. This one corresponds to minus 150, and then we have 650 and minus 650. So then we have component at 650 and minus 650. Now it is said that it is being passed through a low pass filter of cutoff frequency 500 Hertz. So that ends somewhere here. Let me paint it with a different color. So this is here, it's going to end. This is 500. This is minus 500. So you can see that only sinusoid components that are being present are 150 Hertz and 250 Hertz, because anyway it's a low pass filter with cutoff frequency 500, so 650s are anyway going to be ruled out, they will be blocked. So only sinusoids we'll have is 150 and 250 Hertz, and there should be an answer corresponds to that. Yeah, the first one. So when you sample using this sampling frequency of 400 Hertz and pass through a low pass filter with a cutoff frequency 500 Hertz, so these are the sinusoids. You will be left with two sinusoids, one at 150, another at 250 Hertz. So let us move to our next question, which is MT is 50 sync 25T. Just a moment. Okay, MT is equal to 50 sync 25T, which means 2 sine 25 pi t by pi t. So basically this is a sync pulse whose amplitude vary between 2 and minus 2, and of course in frequency domain if we talk about, so this one here, frequency domain, spectrum is going to be a rectangular pulse whose 1 sided bandwidth. By the way, when I say one-sided bandwidth, I mean by that, so let's say this is the rectangular pulse we are going to obtain, which actual bandwidth is fs by 2 to fs over 2. So two-sided bandwidth is fs, but we are concerned about this one-sided bandwidth, so this fs over 2 is what I mean by one-sided bandwidth. So the one-sided bandwidth is given by 12.5 hertz, and this is also the maximum frequency component of this message signal, and so you can call it FM also. This is FM. So if my message signal has maximum frequency component of 12.5 hertz, so the minimum sampling rate I will require for this signal while moving from analog to digital domain, I also want to avoid aliasing. So I have no option but to sample at minimum at the Nyquist rate, which is twice this maximum frequency component, that is 25 hertz. So Nyquist rate 2 times FM 2 times 12.5, that is 25 hertz, the first option here. So we are consider a signal MT, that is band limited to frequency FM, and the minimum sampling rate required to sample this signal to avoid spectral distortion is, again that is a similar question only. The answer is 2 FM here. Sorry, I was marking both. It should be 2 FM. And the last question is about consider a signal MT, which is a spectrum MF, which is sampled with an ideal impulse strength of sampling frequency Fs. So what should be the spectrum of the resulting sampled signal? So that already we have seen, but I will just briefly write down how we are getting there. So first we have this analog signal, MT, and then you sample with impulse train of sampling period Ts. So what we get from there is this M NTS times del n minus sorry T minus NTS. So this is my sampled signal, so I need its spectrum. So when I look for the spectrum, that is M delta F, it is a convolution of the original signal spectrum with that of Fourier spectrum of the impulse train, Fourier transform of the impulse train, which turns out to be another impulse train in the frequency domain with fundamental frequency Fs, which is just the inverse of the fundamental sampling period. So we are left with this del F minus n Fs. So this is a function of f, this is a function of f, so this is a impulse. So when you are convoluting any function with the impulse, what we will end up with is m delta f is equal to the scaling factor fs times integral, sorry, summation, and the shifted version of the original spectrum by integer multiple of the sampling frequency. So this is going to be the spectrum of the sampled signal in terms of the original spectrum. So we have already derived it's like in lectures it has been derived in details, and also while discussing the first question here I just repeated it, so I won't repeat here it again. So the answer you can see clearly is this part, the second one. So this is pretty much all for today. So if you have any question regarding the today's problem solving, or any question in general, I will be happy to answer, like of course if I can. Otherwise we can just conclude the session. And Sanjeevi, I will get back to you with your query. Like for that, I need to first brush up my basics. But once I do that, I will get back to you over email. I have noted down the address. So, any question here regarding the content of week 7 or the problems that I have discussed here? If you don't have any question, then we can conclude the session, but I'll just encourage you to ask if you have any question in mind, like regarding the content of this week or these problems, or any questions in general that like I will try to answer to best of my capability. I'm sorry, am I even audible to you? uh, you guys can hear me, right?
Yes, sir.
Okay, okay, thank you, thank you. So fine, if you guys don't have a question, then we can conclude this session. Thank you all to be with me for this entire session. I like really appreciate it. Okay, so basically I just need to discuss the question because uh, today's live problem solving session, I was like at the initial stage I was discussing something with one students and I forgot to turn on the recorder. So actually it turns out first 1 hour of discussion is not being recorded, so that is why I plan to discuss that part again and record it so that you can have those recorded lecture available anytime, otherwise it won't be available to you. So I guess I started recording somewhere from, just let me check once. So up to this ninth slide I haven't discussed most likely, so I plan to talk about what I did in those first 1 hour briefly so that if you have an idea of the same. Okay, so first we are given a particular signal and we are asked what are the minimum sampling rate required for the signal to avoid aliasing. So there are two important part here. First of all, sampling rate, like, and second is aliasing. And why are even more than these terms? So we have to see what those terms actually signify and what they actually mean. Like for example, sampling rate. Why it is even sampling rate is required? So like week 7 and week 6 and week 7 partly they both focus on the analog to digital conversion parts. Like for example, you have analog signal but your processing are mostly done in the digital domain. So basically you have to have a equivalent digital representation of your analog signal. Now when you are moving from analog to digital, so how do you practically achieve that? You have to sample your signal at certain instant, right? Analog signal is right like what, like it's a continuous kind of function of the time, but when you move to the digital domain you work with the discrete values. So actually if you look at this analog signal here, I have drawn here for you, and this is the mt, or you can see this here one here is the mt is a function of t, it's analog signal. So there are infinite points, right? Now when I talk about digital domain, we are talking about finite number of points. So that is why we basically plan to sample the signal at certain interval, right? For example, we plan to, let's say, sample every ts second. like for example we are going to sample every ts second. Well, let's say ts is like 2 millisecond, so every 2 millisecond I am going to sample one point from this message signal. So that is going to be my sampling period. And what is my sampling frequency? So basically that is a measure of how many samples I have every second. So for example, if I sample every 2 millisecond, in 1 second we are left with 1 over 2 times 10 to the power minus 3, 500 samples, right? So if I reduce my sampling period even less, so I will have more number of samples. That means my sampling frequency is going to be high. Sampling frequency is basically a measure of how many samples I have per second. So now why we are so concerned about the sampling rate? So when you actually move from analog to digital domain, you do all the processing, then you have to get back your analog signal, right? So what you want to ensure that when you move between analog to digital domain, your signal is not distorted, or in a bit high level there should be no information loss, right? So from when you move to analog to the digital domain and digital to analog, there should not be any information loss. So in other words, the signal should not be distorted. So how to ensure that? It turns out that actually there is a relation of the sampling rate and the frequency, like your maximum frequency component of your message signal. There is a certain relation, so that you have to avoid aliasing. Aliasing is that part, actually it's more clear if you look at the frequency domain representation of the signal. So let's say you have some frequency domain representation, right? Okay, we'll get there later. So basically you see that aliasing is something that is going to cause distortion to your signal, right? And when your signal is distorted, so that is inevitably going to cause some information loss. So aliasing causes distortion, and distortion causes information loss. So basically that means when you move to analog to digital or digital to analog domain, you are losing some information, and of course you don't want that. So how to ensure that there is no distortion or no aliasing? So that is what is a crisp of a part of week 6 and week 7 lecture, and that is we are going to discuss here briefly in a nutshell. So you see this is the message signal, and we are sampling it every instant here, right? Like at minus 2s, minus ts, at 0, at ts, at 2t. See, 0 is here the reference point. So on the left you have negative on the sampling periods, on the right you have positive multiplicants of sampling period. You can choose 0 here on the left extreme, therefore all there can be negative. You can choose 0 here, therefore all sampling periods here are going to be negative. So it's merely about, not about positive and negative, it's about the where the reference point you are choosing to be. So like for example, fine, you say that I'm going to sample this message signal at every ts second. So this is my sampling period and my sampling frequency is this. Good. Now how do you going to practically achieve that? And this we talk about, let's say this is analog to digital conversion, analog to digital conversion, and aliasing we call it distortion. So you can see here we have this message signal. So what I am planning to do, I am planning to multiply this message signal with a impulse train. You have read about Dirac delta impulse earlier, right? So we are going to multiply this signal with a impulse train. You can see impulses are like uniformly spaced with a gap of ts. So what would that result into if I multiply these two both? So these impulses are of unit amplitude, everything nice and then, but when you multiply with the message signal, what will happen at point minus 2 ts? The impulse will pick the value of the message signal at that particular time instant. Similarly at ts, it is going to pick the value of the message signal at that particular time instant. So what is going to happen when you multiply the message signal with the impulse train is that the impulse amplitude is going to be modulated by the message signal. That is the only thing that is going to happen. Now this impulse train is going to be used for ideal sampling. It is not very practical thing, but theoretically it's for ideal sampling. And you can see this impulse train here is periodic signal, right? It is basically it's repeating every ts second, because you can see this is uniformly spaced, all are identical, only same amplitude, and it's periodic with the fundamental period of ts, right? So it can be written as this kind of thing, del t plus 2s t plus s del t plus t minus s. So you can, in compact notation, you can write this as a infinite impulse train of this kind. So this is what we want to achieve in practice: sample the message signal. And practice, how we do that: we create a impulse train, we have the message signal, we multiply them, and as a result what will happen at those particular sampling instances, the uh, amplitude of the impulses are being modulated by the message signal at those particular point. Now let us see what happens next. Now you are going to multiply the message signal with the impulse train. So mt times g lambda t, right? And g lambda t, we have already seen the infinite impulse train, the compact notation. So this entire thing here, let me point it out, this is infinite impulse train, and this is the message signal mt here. So this is the time domain signal, this is the time domain signal, and you know that when you multiply the any signal with a impulse shifted at a particular time instant, you basically pick the value of this particular signal at those time instant. So that is what going to happen, because all other cases, this apart from this point, this integer multiple of sampling period, the delta function takes zero value. So only the function, only the value of m at that particular uh, time point, that is integer multiple of sampling period, this is going to be picked, and rest is going to be 0. So this is going to happen. Okay, there should be a summation here, this I missed, should not have done that. So this should be a summation over infinity, and this is what you get as your sample signal. You can see the impulses are still remains uh, uniformly spaced, but the periodicity is gone. Why? Because now the amplitude is modulated by the corresponding amplitude of the message signal, so no periodicity is there. So the sampled signal is now not anymore periodic. So now what is going to be, so when you talk about this aliasing and distortion and all that, it's always better to look at the frequency domain, because then it's easy to express what do I mean by information content, what do I mean by distortion, what do I mean by recovering the signal properly without aliasing. These all the terms that are applicable in the frequency domain. So we need to go for the Fourier transform, the frequency domain representation of the sampled signal. So what is going to be, so in time domain it's a multiplication between the message signal and the infinite impulse train. So the frequency domain is going to be the convolution between the Fourier transform of the message signal and the Fourier transform of the impulse train. So we have already observed the infinite impulse train is a periodic signal with fundamental period Ts, right? So if it's a periodic signal with fundamental period Tf, okay, by the then we should have a Fourier series representation of the same. By the way, we have already drawn the spectrum of the original message, so this is what it looks like. Its maximum frequency component is Fm. Now again back to this thing, like in this impulse train is periodic before multiplying with the original message signal, so it's have a fundamental period 2s, so we can have a Fourier series representation which basically express this infinite impulse train as a sum of discrete spectral components which have the corresponding amplitude Cns, where Cn corresponds to the strength of the signal at that frequency component, which corresponds to the n times the sampling frequency, right? So we have this infinite impulse train Fourier series representation. So what we need to calculate is this Cns only, the amplitudes. And how do we compute that? So for that we look at this expression. That's pretty straightforward. It's 1 over the Ts, and we have to 1 over the fundamental period, and we have to integrate over one fundamental period, be it from 0 to Ts or minus Ts to 2 Ts by 2, doesn't really matter. Then we will integrate with the complex conjugate of the exponential and integrate it over the region. So this is the infinite impulse train, right? So over this integration limit, so I'll just write this is actually a infinite summation of integral, but over this limit we can see, if we write the spectrum of this infinite impulse train in the time domain, what I will see that there is a impulse at 0, another at Ts, another at minus Ts. So when you talk about this integral limit minus Ts by 2 to Ts by 2, there is only one impulse which is at 0, and everywhere else the function has a 0 value. So comfortably in this limit we can replace g lambda t with the del t function, right? And what we'll have, this del t takes value of 0 only, sorry, 1 only when t is 0, and all other places it's 0. So this integration basically reduces to the power minus j pi 2 5 s t at a value t is equal to 0, and from there we'll see that the amplitude at the different spectral components actually doesn't depends upon that frequency component n. N dictates the integer multiplier of the fundamental frequency. So Cn corresponds to the amplitude spectrum amplitude of the, or the strength of the nth frequency component, but it turns out it doesn't depends upon n. It has a uniform amplitude over the all spectra. So the infinite impulse train can be written as follows: sum over n is equal to minus infinity to infinity, that is at all integer multiples of the fundamental sampling frequency, the amplitude is same, that is 1 over Ts. And now when we take the Fourier transform of the same, we can see this is sum of infinite number of complex conjugate, right? This is infinite sum of complex conjugate. And what is the Fourier transform of the complex conjugate? It is a shifted impulse. And what is the amount of shift? That is the frequency of the complex conjugate. Frequency of the complex sinusoid. So whenever you have a complex sinusoid in time domain, its frequency domain representation is going to be a shifted impulse, but the shift amount is the frequency of that complex sinusoid. Similarly, in the frequency domain, if you have a complex sinusoid, its time domain representation by the uh, duality theorem is going to be a shifted impulse. The same apply here. It's a sum of infinite number of complex sinusoid. So we have seen the infinite impulse train can be written as a infinite sum of complex sinusoid that has a Fourier transform of infinite impulse train in the frequency domain also, or the shift or the frequency parts where the spikes happen. Of course, they are the integer multiples of sampling frequency. So that is what being observed here. So infinite impulse train in time domain as a frequency domain representation as infinite impulse train again in frequency domain. The only thing is, in the time scale, in the time domain the spacing is Ts, in the frequency domain the spacing is Fs, which is 1 over Ts. So for example, in if the spacing in the time domain decreases, that is the impulses become more dense or close to each other, in frequency domain they will be more space, that is 1 over Ts will increase actually if Ts falls. So in the time domain, if uh, the gap between the impulses shrink, in the frequency domain the gap will expand, and in the time domain if the gap increases, that is the your sampling period is more, then your sampling frequency will be less here, and sorry, your TS when increases, then you'll have in frequency domain the impulses are going to be much more dense, that is the gapping between them is going to be small. So this is the only difference. Otherwise infinite impulse train in time domain will have a frequency domain representation of infinite impulse train again. So you can see this is the frequency domain representation of the sampled signal, which can be given as the original spectrum of the message signal MT, convolution with spectrum of the periodic impulse train. Why convolution? You can see here in time domain, sorry, just a moment, here in time domain it's multiplication. In time domain it's a multiplication between the message signal and the periodic impulse train. Therefore when you move to the frequency domain, it's going to be convolution. So convolution with what? With another impulse train of the original spectrum. So this is a function of frequency, this is a function of frequency again. So what you are going to observe here, so these are basically convolution with the shifted impulse going to result into the shifted original spectrum. So basically you are left with, you see, some scaling factor and infinite copies of the original spectrum that are been shifted by integer multiples of sampling frequency. So that is the main intuitive understanding, that this is your sample spectrum of sampled signal, which is nothing but a scaled version of infinite number of shifted spectral copies of the original spectrum, message spectrum MF. So this is your original message spectrum MF, and when you actually sample it with sampling frequency Fs, what you are end up with in frequency domain, multiple copies with it. Of course there is a scale version which I am ignoring for the moment, because that is not as much important as the gap between here. So there are multiple copies here which is shifted by a frequency Fs. Now the important thing is the aliasing thing comes here. So what they call as aliasing or distortion, that happen once you can see this is shifted version, first shifted version of by the frequency Fs, right? So therefore this part here will be at Fs minus Fm, and this one which is not shifted, the baseband component is the reaches here at Fm. So what happens that this point comes on the left hand side of this point, this is being shown here, that Fs minus Fm is less than Fm. Under this condition what will happen, that these two spectral copies overlap. So two spectral copies overlap, and this we term as aliasing. This is termed as aliasing. So here you can see these two copies overlap under this condition here, and this corresponds to when the sampling frequency is less than twice the message frequency. So then what will happen, your two spectral copies are overlapping on top of each other, aliasing is going to happen. Now you cannot recover the original message signal because it is already contaminated by the copy in this particular part. You are fine with this part, but you cannot get the whole undistorted signal because this part is already being distorted by another spectral copy. So this is what we are going to call aliasing, and that happen when frequency sampling frequency is less than twice the maximum signal message frequency component. And to ensure when it doesn't happen, like for this case when this doesn't happen, so that there is no overlap, spectral copies are kind of not overlapping with each other, when this will happen, when this condition is being satisfied, and that corresponds to Fs greater than equal to 2 Fm. that is sampling frequency is greater than or equal to twice the maximum frequency component of the message signal, then there is going to be no overlap, and this is what is called Nyquist criteria. So under this condition, what you can do if there is no overlap, so there are none of them is interfering with each other, so what you can do, you have this sampled signal spectrum, and then you pass it through a low pass filter with a cutoff frequency somewhere this. So in that way it is going to block this, this and this, only let pass this. And what is this? This is your original message spectrum. So you are actually able to get your original message spectrum undistorted, no overlapping, no one is interfering with it. So you can see there is no information loss, you get back what you started with, and that is only ensured when the sampling frequency is greater than twice the maximum message frequency. Then only it is ensured that you can actually use a low pass filter with a cutoff frequency of fs by 2 and recover the undistorted message signal. But the moment your sampling frequency is less than twice the maximum frequency component of message signal, then the spectral copies will overlap and you cannot anymore recover the undistorted spectrum, because it is already being contaminated here by another copy. So this is the key understanding in the whole part. And once we obtain that, we are easy to get the answer here. So just let me go to the answer part here. Where is that? Yeah. So now you can see that clearly you can see what is the minimum sampling rate required for signal to avoid aliasing. We will look at the signal first. What's its the maximum frequency component? It turns out to be it's 250 Hz. So you know now from Nyquist criteria that my sampling frequency need to be at least greater than or equal to twice the maximum frequency component of the message signal. The maximum frequency component of message signal is 250 Hz, so I need twice of that, that is 500 Hz should be my minimum sampling rate to ensure that. In practice we actually keep a buffered zone, that is you don't actually go for exact twice the maximum frequency, you go for more than that. For example, in this case you have a 250 Hz, so twice of that is 500, so maybe you go for a 600 Hz of sampling frequency to ensure that there is no aliasing or no distortion. But in theory at least you need 500 Hz to ensure that there is no aliasing. And I am yet discuss this question also. So this is actually regarding that here they say that bandwidth signal is already sampled at a rate greater than the Nyquist rate. So we have satisfied the Nyquist criteria. You can actually pass it through a low pass filter and get the original signal back in the undistorted manner, so that there is no information loss. So we have to start from exactly where we left. So here the information is given that the band limited signal is sampled at a rate greater than the Nyquist rate. So what does it mean? It means that your Fs is greater than twice the maximum frequency component, that is Fs is greater than twice Fm. So when Fs is greater than twice Fm, so your sampled signal spectrum is going to look like this, right? Because your Fs minus Fm is greater than Fm, so that is what this condition is. So therefore the spectral copies are not interfering with each other, so they are nice and all. So what you all need to do, you need to pass this sample signals through a low pass filter of cutoff frequency Fs by 2. Fs by 2 is going to be somewhere here, is this condition is satisfied somewhere between Fm and Fs minus Fm. And when you pass this through a low pass filter, what we will obtain, it is basically filter out these two component, like basically what I mean by filter out, it blocks these two and will let pass only this thing. And of course we are going to apply amplitude. The low pass filter have amplitude of 1 over Fs to balance the scaled the scaling factor that is introduced by sampling here, that is fs. You have a low pass filter has the amplitude of 1 over fs, so they will basically cancel out, so you'll get the original message spectrum here. So we are basically passing the sample signal to a low pass filter with cutoff frequency fs over 2 and magnitude 1 over fs. Cutoff frequency fs over 2 ensure that only the original baseband message spectrum pass through in the undistorted manner, and the magnitude ensures that the scaling factor that is caused by the sampling, that effect is being nullified, so you can get the original message spectrum back. So this is the HF, it's a low pass frequency response, which should be a rectangular pulse with cutoff frequency fs over 2. So we pretty much know, so this is the condition of low pass filter frequency response. So we know in our rectangular pulse in frequency domain, in time domain, what is going to be, it's going to be a sync pulse, right? So this is the time domain response of the low pass filter. So why we are need this, because this here it's talk about the original signal, how it can be deconstructed from the sample via interpolation. So this is actually you're passing the sampled signal through the low pass filter to get the original spectrum. So this has a nice frequency rectangular pulse frequency response, so which has a time domain equivalent response of a sync pulse. So basically this sampled signal is passed through this HT here, which we will show next. So the reconstruction block will talk about that. So it's a reconstruction block we are talking about. We have the sample signal we are passing through low pass filter, which has a time domain response as a sync pulse to obtain the original message signal. So we are passing through a low pass filter, so in time domain it's a convolution between the sampled signal and the time domain response of the low pass filter. So how do we express that? So this is my sampled signal expression, and we are convoluting it with the sync function. So this part mnts, it's basically the value of m at the integer multiple of the sampling period. So this part is constant, and this is a time domain signal, the impulse function, and this is also a time domain signal. So basically when you are convoluting with the shifted impulse response, basically the shift is being transferred to your original signal. That is what is happening here. The sync function, this is a shifted sync function. Let me point it out here, shifted sync function, and this part remains. So sync function, you can see now not only being shifted, its amplitude is also being modified accordingly. So based on the shift value of the sync function, the amplitude is being picked. For example, if it's shifted by n times the sampling period, its amplitude is now the message signal value at n times the sampling period. So these are, you can see, infinite number of shifted sync function and amplitude infinite sum of infinite number of amplitude modulated shifted sync function. So you can see here, this is being pointed out, the shifted sync pulse by NTS and amplitude are scaled by the corresponding message values at those particular time instant. So you can actually go one step further, and here you can write fs and ts, and fs and ts are just result into 1 because ts is 1 over fs. So this is what you will obtain, and this is the reconstructed original message signal. So this will geometrically it will look something like that. So this is the sync pulse corresponds to m0. You can see this is the point where it is being sampled, and this is the sync pulse corresponds to m at the first sampling period, and this is at m is equal to minus ts. The point to observe here is at this point the sync function corresponds to n is equal to 0 is being sampled, right? And at this point you can observe the contribution of other sync pulse is actually 0 at this particular sampling point, and this is being ensured by the Nyquist criteria. Similarly, when you talk about the sampling point corresponds to TS, you can see here the contribution of the other sync pulses is 0, and similarly for minus TS here also the contribution of other sync pulses is 0, and that is being ensured only when the Nyquist criteria is met. If the Nyquist criteria is not met, you can see at this sampling point the contribution from other uh, sync pulses is going to be non-zero, and that is going to distort your the original message reconstruction. So based on this infinite number of sync pulse, you can actually get your message back. So since this is a sync function sync pulse based interpolation, so the interpolation filter, you can see it's called sync interpolation. So therefore it's called as a sync for ideal sampling case with impulses, the original signal can be reconstructed from the samples via interpolation using the sync pulse. An original message you can see by adding these points, you can actually get the original message signal empty. I think to this point only I had missed the recording. After that I started, but I just cannot remember exactly. So let me also explain this part also, just to be ensured that no part is being left from explanation. So here basically we are asked to consider a sinusoid signal empty, that is cos 5000 pi t, and it is being sampled using a impulse train with sampling frequency of 8 kilohertz, and it followed by a low pass filtering with an ideal low pass filter of 11 kilohertz. So what are the frequencies of sinusoid being present in the resulting signal? So the message signal, we can see that cos function we can write as a sum of two complex sinusoids, and we have written that, and then we use this property that complex sinusoid in time domain refers to shifted impulse in frequency domain. So therefore if I go for the Fourier transform of this, I'll obtain two impulses at minus 2.5 kilohertz and 2.5 kilohertz, and this is the original message spectrum for us. Now it is being sampled using a impulse train with sampling frequency fs. We know what happens when you sample with a impulse train with a particular sampling frequency. Basically we are going to create infinite number of copies of the original spectrum with a scaled version of the same. So for a moment we forget the scaling version because that is less important. We focus on the shifted version of the, we forget the scaling constant, ignore that part, and focus on the shifted version of the original copies. So here we get all these values. So this first two corresponds to m is equal to f, where that shift is by 0 frequency, that is the baseband component, and then comes the shift by 8000, and then it comes by the shift by 2fs. Here fs is 8 kilohertz, so f minus fs, this one is the, this 2 corresponds to m f minus fs, and this 2 corresponds to m f minus 2 fs. Similarly this 2 here corresponds to m f plus fs, and this one and this one corresponds to m f plus 2 fs. So doing that, we have seen that this corresponds to impulse at 2.5k, this corresponds to impulse at 10.5k, this corresponds to impulse at 5.5k, this 2 corresponds to impulse at 18.5 and 13.5, and this here corresponds to minus 5.5 and minus 10.5. This one here corresponds to minus 13.5, and this one is corresponds to minus 18 point, minus 18.5. So if I plan to draw the sample signal spectrum, it would look something like that. You have a impulse at 2.5 kilohertz, 5.5, 10.5, 13.5, 18.5, and similarly on the negative domain also. Now it is being said it is passed through a low pass filter with a cutoff frequency of 11 kilohertz. So if you draw this rectangular box here with a width of 11 kilohertz, and so basically it's going to block the components outside 11 kilohertz and let the component inside pass. So we can see there are three distinct sinusoid at three different frequencies. One at 2.5, another one is 5.5, another one is 10.5. So these three sinusoids we are going to find at the output of this low pass filter with cutoff frequency 11 kilohertz. So therefore this is the answer: 2.5 kilohertz, 5.5 kilohertz and 10.5 kilohertz. Here we can see that we are asking about the minimum sampling rate required to avoid aliasing for the signal MT. So the MT expression is a bit tricky. Here you can see it's sinc 20 pi t. So sinc of x is actually sinc sine of pi x by x. So sinc of 20 pi t means, if I write about only the sine part, it's sine 20 pi square t. So your frequency is now 10 pi. So sync pulse in time domain, frequency domain, corresponds to rectangular pulse, and the one-sided bandwidth is going to be 10 pi, right? Now if I have multiplication in time domain, that is sync cube here. So we have convolution in frequency domain, and with PMF with 3 times with itself. Now we can see that convolution increases the bandwidth in an additive manner, and each one of them has a bandwidth of one-sided bandwidth of 10 pi. So if you convolve 2 times with itself, so it's going to be the bandwidth will expands to 3 times 10 pi. That is your one-sided bandwidth for the equivalent frequency domain representation is going to be 30 pi. That you can see from here also. Sync, if I talk about the sine part only, it's sine cube. So that is some scale version of sine 3x. So your bandwidth now become 3 times of that. So important thing is the one-sided bandwidth is 30 pi. So that is your maximum frequency component FM. So your minimum sampling rate is going to be twice of that, and so therefore your answer is 60 pi hertz. So I guess this point onwards is being captured in the lecture in full details. So I'd like to stop here. Sorry for the inconvenience caused, because the like ideally I should have recorded it from the very beginning, but I just forgot. Unfortunately I remember at least within an hour, otherwise I have to record the whole session again. But fine, I guess this should be helpful to you, and if you have any doubts or if you have find any uh, errors in the problem solving, please let me know via the comments section in the YouTube. So thank you. I'm ending the session here.